Okay, so good morning, everybody. We are having the seminar talk from Dr. J.O. Wu. He is presently a research scientist from Samsung SDS Research. And just on the note, he asked me to mention he's going to join Amazon Science, AWS, and AI next month, starting next month. So, as in Dr. Wu's background, a very short introduction that he got a PhD in applied mathematics from PL, and before that, he did his undergraduate from KAIST, so Korean Advanced Institute of Science and Technology. He published in both mathematics as well as very top tier AI venues. So one of his paper got the top 25% ICLR selection. So ICLR has in the Google Scholar metric rank 9 across all conferences and journal across all fields. And he also got a paper in ICCV. And his research won 2018 VHP Innovation Awards first prize. So without any further ado, I will let Dr. Wu to talk about quantifying uncertainties of deep neural networks and its application. Please.
Okay, yeah, thanks so much for the invitation. And it's really, I really appreciate for having this opportunity. Yeah, as Dr. Dutta said, I will make a transition next month to the AWS, Amazon Science, but that does not mean I'll stay there forever. I think it's a very good opportunity to make a transition before the moving into the academia. So, I mean, okay. So, yeah. So today, I want to talk about the quantifying uncertainty of deep neural networks and its application. So this is really about my main research topic, and I really want to pursue more and about by using or the uncertainty. So I want to give you. I know this is the math department, so people talk about the proof. So I was trained as a mathematician, but today it will be much more high level. It will not be that much deeper. So I just want to give you some introduction about my previous research and also sort of ongoing research. And then maybe if I have some time, I also want to talk about some future research. Okay. So okay. So then I want to talk about what's the brief introduction about the uncertainty. What is uncertainty? So I just asked the ChatGPT about to generate some images. Now I think yeah, many people already know about this ChatGPT and DALL-E to image generation. So then just give you some idea what's the uncertainty. So as I title and I briefly mentioned about this, uncertainty is a lack of predictability in understanding or forecasting outcomes encompassing both unknowable randomness and reducible knowledge gap. So that's really about sort of the unknown thing. So how because future they're not predictable, so it's very hard to uh, know about the outcome. So every day we are facing some sort of uncertainty. So then yeah, ask the GPT the uncertainty of large language model just generate this kind of images, and the uncertainty of our life can be sometimes the bright future, sometimes can be the dark future, but sort of mix the things exist. So always we have to deal with this kind of the randomness or the different situation in the future. I mean, deep learning research, we also have to deal with something similar situation like this. So just want to give you some yeah brief introduction, give you some idea uh, about this. So then in the traditional the research community, people have focused on the two different type of uncertainty. One is the model uncertainty. So I call it epistemic. They call it an epistemic uncertainty. So epistemic uncertainty is the uncertainty in the knowledge due to lack of information, but it can be reduced through the learning. So if you look at this image, I'll ask the GPT to generate these images. So then if you look at this image, there's some formula or some sort of as a human, we are looking at the universe, the sky. So even though we do not know the exactly what the universe looks like, but still, if we observe or study more, eventually we hope that we know that we will understand how the universe looks like or how the formula we can discover more. So this model uncertainty or epistemic uncertainty really is something about we can reduce the uncertainty if we have more information. So that's sort of yeah the uncertainty people describe as a model uncertainty or the epistemic uncertainty. I just want to give you the idea. And the other one is called the data uncertainty, and sometimes in the uncertainty community they call it as a aleatory uncertainty. And then yes, I mean just want to show some picture, just give you some interest. So so then as you can see these images, the one half side it shows very sort of the bright and shiny things, and the other side it shows us something like the thunderstorm and very the dark images. So that and also in the middle it shows some blue. That is randomness. So then the aleatoric uncertainty is really talking about something an inherent randomness within the data. So this one, if you look at the sentence here, there's an inherent randomness in the system. So we cannot remove this kind of the randomness or uncertainty by even though we add more information. So it's a sort of noisiness, really the inherent randomness in the system or the data. So then we cannot reduce it. So then those kind of the uncertainties called the aleatory uncertainty. So then yeah, those two epistemic or model uncertainty or the data or lateral uncertainty, these kind of the main concept when people talk about the uncertainty. So then I was thinking about the but as a mathematician, when I started from this uncertainty formula, people just try to decompose in this way. The one is uncertainty like can be decomposed into model uncertainty and the data uncertainty, the epistemic and aleatory. We can just decompose in two ways. But then when I look at the as a mathematician and information theorist, when I look at the formula of this, I can reformulate, rewrite down this uncertainty this way. One is the total uncertainty is sort of the entropy of the system, and then the model uncertainty can be thought as a model, the mutual information between model and the label. And then the other side, data uncertainty, I can reformulate as a conditional entropy. So then when I first look at this formula, because it's very, I mean, if you just write down the formula, it's very, very simple. If you look at the information theory book, it's just at the very beginning, you see this information, the mutual information plus conditional entropy that can decompose in this way. But as a mathematician, when I look at this formula itself, the more interesting part was in the deep neural network in the AI case, a model is typically modeled as a continuous structure. But then in the classification problem, mostly in this label or the other side, can be modeled in a discrete structure. So then even though with that kind of continuous and discrete structure, um, we can still define the mutual information and conditional entropy. But then in the information theorist perspective, I mean, they are not that much well studied how we can combine this continuous and discrete structure together. But that's how I was, why I was thinking about maybe there can be thinking about some question like, oh, maybe there can be something more than this because we don't know much about continuous and discrete combination together. But then we can still write down this formula, this mutual information conditional entropy. So then yeah, maybe yeah, that's sort of the starting point when I think about this the problem or uncertainty problem. Maybe I can, as a mathematician, maybe I can do something more, something better than this. So then that's how yeah I got started about this research.
So in engineering, there's a discussion called Kalman filter.
Yeah.
So Kalman filter is similar thing that there is the measurement, which is like a data, and comes with the covariance matrix. And there's a model, and that also has some uncertainties, covariance matrix.
Yes.
Then based on that, you estimate a new state of the model based on the uncertainty in the data in the model. So are you do you know Kalman filter and you can relate to that?
Oh, at that time, yeah, I mean, I heard about the karma filter
Yeah.
before, but I didn't have much good understanding about that. So at that time, yeah, I didn't fully try to connect them with the karma filter. Yeah, definitely, I want to explore more, but yeah, still I'm not that much have a good experience in the Kalman filter, yeah, point of view yet. So okay, so then yeah, so then I was, I mean, as a mathematical structure, there was some stochastic process is called the point process. Point process is more about the combination of the continuous structure and the discrete structure because it's a, for example, like Poisson point process, we have a sort of random number of the point, but then the underlying of those kind of number and the location wise, there's some continuous structure there. But then when I was a postdoc, I mostly focused on that kind of information measure of the point process itself. And then that's how when I saw some overlap with my previous background and also see this kind of uncertainty structure. And then when I think about try to think about something more about this problem, and that's how I was trying to propose this balance entropy in the active learning perspective. So I will come back this one later, but just give you some overview about this the balance entropy. I just want to introduce this first, and I will come back this again. So balance entropy is sort of the combination of the combine trying to combine those two uncertainties together in some sense. I mean, I cannot exactly say there's no mathematical proof that oh this is really the combination of the epistemic aleatoric, but when I also try to understand this measure more and more, and really sort of in the middle of those two uncertainty. So then it actually the sort of because I'm also considering the continuous structure more. So anyway, so if you look at this in the middle, that there's some continuous entropy formula is in the middle, and also the discrete entropy formula is there. So then it just try to combine them together. And also the good perspective here is there's some because it's based on sort of Bayesian neural network, and there's something like there's a formula also involves some the posterior distribution of some the underlying distribution. So it's the PI plus what I mean by sort of posterior distribution. So it's also looking at some the next step or the future. So what if I add this information there, then how much information or entropy I can see. So those kind of formulas also embedded in here. I was also just try to combine them together. So I will come back this formula again, and then this one is really the my main research, previous research, and it was accepted in the ICLR last year. There was also selected as a top 25%. Okay. So so yeah, I just want to give you some brief motivation why the uncertainty is very important. So I mean, this paper now is slightly outdated, but still I think it's a good paper to just introduce. So people, I mean, the computer vision people, especially in the value network, when you look at the probability output, then mostly they are pretty much overconfident. And also in the large language model, you see a lot of, I mean, even though it gives you the wrong or answer, but still, if you look at the probability of the neural network itself, they are very, very high probability. So there's some overconfidence issue people already know about. And but then one way to mitigate that one is this kind of overconfident issue is the making the neural network as a Bayesian. So that's sort of the paper title talking about being Bayesian, even just a bit fixes overconfidence. But I mean, they said it's a fix, but I cannot say it's a fix. It's still is an unsolved problem. So at least I can say so mitigate the overconfidence. But then one of the key idea is that they can try to make this neural network as a Bayesian. So in the last layer, Bayesian is enough. Okay. So then also the very recently in the ICML, there's a positional paper track. The positional paper is more about, it's not about, okay, we discovered the new idea. It's not like that. Position is that they really have some position about our future direction. But then nowadays, we are talking about the large language model, but we still see that when we interact with the ChatGPT or other like the Gemini, but then we still see a lot of the hallucination problem. So they just give some example in this paper. I mean, I cannot say this one's accepted because ICML review will be released 2 weeks later. So I assume that they submitted there. So if you look at that their example, there's an answer. I mean, For example, like there are some question. It's some chemical, they have some chemical formula, and then is this really the correct name of that chemical formula? Then actually the correct answer is wrong. It is a sulfuric acid or osmium tetroxide. I don't know what it is, but if you look at this example, but then if you ask this one to the ChatGPT or Bing Chat, it's combined, it's integrated with the ChatGPT, and also Llama 70 billion. Actually, the language model said they are very, very confident about the output. Also, they actually hallucinate you about the answer. So their answer is not correct, but still, nevertheless, they said they have a very high confidence. But then, even though it's not true, so then what this a lot of people in the Bayesian uncertainty community they talk about is we have to employ or use the Bayesian neural network, Bayesian deep neural network will mitigate this kind of hallucination issue. So I think my research also aligned with this kind of the line of the research. So I also want to pursue this kind of the hallucination, reducing, mitigating the hallucination issue. Not only in the language model, maybe now we are moving on to the multimodal the model. That's why yeah, this uncertainty is a very important. And also I think it's 2 weeks ago, the more than 2 weeks, almost a month ago, the Air Canada, they actually deployed the chatbot system. But then when the chatbot customer, one customer was in touch with that chatbot, and then that chatbot suggested some the recommendation, wrong information, inaccurate information to the customer. And then that customer followed the wrong instruction, and then tried to ask for some refund following some instruction. But then the Air Canada actually refused based on their own policy. But then the real problem was the chatbot gave the wrong information. So then the customer was misled by the chatbot's suggestion. So then eventually the Air Canada has to give the refund to the customer. So still, yeah, the hallucination problem is very critical. And then actually, what Air Canada did was they actually abandoned, removed the deployed chatbot because of this kind of the hallucination problem. So so still, yeah, this is the existing problem. Nobody actually solved that problem. That's why I think also the autonomous vehicle the system is still we have to move and we have to develop further. So then to make it much better and better, we really need to understand what's the uncertainty or how to mitigate this kind of the hallucination problem or the wrong prediction problem more and more. So that's why the uncertainty is very important. Okay, so then yeah, I just want to give you some uh, now I move on to the real application. So application is more about, I want to talk about my previous research, the active learning part. So I want to give you some brief idea first, and then a little more detail about the active learning. And then I want to move on to my recent topic. So, okay, so that's the active learning. Um, so yeah, I'm just using the same slide when I used in the ICLR, but yeah, just give you the idea about what's active learning for those of you who might not be familiar with it. So basically, active learning, I want to reduce the training data set size. So typically, when we build some models, we have a lot of unlabeled data. So I mean, most cases, yeah, we only have the images. We don't know what the label, ground truth label is because depending on the application, the label also can be different. But still, yeah, even though we have a lot of images, so we have to figure out what will be the ground source label. Okay, but then so then the real problem in practice is uh, the labeling itself requires a lot of cost. It's very, very expensive. For example, if you think about the medical, the imaging domain, so doctor they have to annotate the ground truth label, but they are very, very expensive. So because of that, if you think about some more than a million or trillion size of the its scale, I mean it's almost impossible to give the ground truth label to all the images. But because of that, we really need to reduce the labeling data set size. So that's why how I can say call it as I can improve the data efficiency. So that, yeah, this is, and then active learning is a way to improve that data efficiency or reducing the data set size. And then by reducing the data set size, I can reduce the labeling cost as well. So then this is sort of the mechanism framework how we can apply the active learning. So here, so I starting from the a lot of unlabeled data, and then typically we start from some random selection, like select some data point, which data needs to be acquired. Acquired means that we will which data we want gives a label. So after that, the given that selection point, the human or the expert, they give some ground truth label. For example, like this one is a cell or the benign cell or malignant or tumor cell, then doctor can annotate which image will be the more which images will be the malignant case or tumor case, but then it requires a code. So then, but starting from very small data set size, and then we train the neural network. After that, given that neural network, we can actually select which data need to be labeled next, because neural network actually, given this initial batch of the data and then the initial we train the model, that neural network can give us some idea about which data will be much more important from that neural network perspective. So if we choose the next batch of the labeling data, then we do this step again, like the doctor or a specialist gives some labels, and then we train the model. If we do this kind of iteration, uh, more and more. Eventually, this neural network has some sort of saturated performance. And at that time, at that moment, we can start this labeling process. Then mostly in the classification, we can reduce the data set size. I mean, at best, I've seen it's sort of, yeah, I mean, the MNIST is really simple example, but in practice, at best, we can reduce the data set size almost like 90%. That's a really good scenario. But in the segmentation, in the image segmentation case, in the if you think about the pixel level annotation, then we can even reduce more than like 90%, mostly like 99.99%, because in the image segmentation, there's a lot of redundant pixel exists. So then if you only count how many pixels will be required to achieve the almost the highest accuracy, then we can almost reduce the 99.99% of the information. So it's, I mean, mathematically, it's really about the selecting the most informative data or the removing the redundancy. So data set wise size reduction or compression of the information. So, but then in practice, the implication is we can reduce or save a lot of cost in the labeling. So that's why I think that this problem itself is very interesting. And also, I mean, so then the most important step is actually the which data need to be selected or annotated, given some criteria. So then, yeah, so in the active learning, so I have to design, so if I have to come up with some new idea, then I have to design the new way of the quantifying some measure which data needs to be selected first. So then the question is, okay, what is the most informative data uh, among the existing data points? So then we have to consider three different aspects. The one is we have to think about, okay, I want to maximize the information gain, because this is actually what we intuitively we can just think about it. Okay, I want to maximize I want to select the most informative data. But then the problem is that in this scenario is that um, if we think about this problem, the most informative data and the second most informative data, if we think about those kind of two cases, in most cases they are very similar. So the information is really redundant if you look at the entire data set. So because of that, the people have to think about, okay, we need to diversify this selection. So diversification is also very important to reduce the redundancy of the information or to remove the data set size. So then but if we think about the diversification, the problem of diversification is it requires a lot of computational code. I mean, at least just if you just put, okay, I have a bunch of computational resources, I can wait some time to get the output. I know to get the diversified output, but still sometimes because if you really want to diversify the selection, we also have to think about the pairwise distance or the correlation or relationship between those 2 points. But still, if you have more than like nowadays like trillion token size, then if you think about the pairwise correlation relationship between those kind of the high scale, still, yeah, it requires a lot of computational code. So we also want to minimize this computational code, but still we want to achieve the diversification and maximizing the information gain. So we have to consider those three aspects simultaneously. So, but then mostly, I mean, if you look at the previous research, mostly we can easily achieve two aspects. So one way is just, okay, looking at some mutual information or entropy. I don't want to talk about the details about this, but we can just achieve by just selecting some high information gain and also just linearly computation, linear computation of course. We can also achieve, I mean, we can select a point, but still in such a case, we cannot diversify the selection because of that there still exists some data redundancy in the selection. But because of that, if some of people just thinking about some diversification, like batch and batch bar or core set, a lot of different idea. But then in such a case, we still lose some computational cost. So so then the one of the existing idea to achieve those three aspects simultaneously is called the power bar. The bar, let me just go back. The bar is more about the mutual information. Mutual information is really talking about the information gained directly. So then power bar is sort of the randomized the selection given the mutual information or information gain. So they just try to randomize the selection. But then if you really try to apply that idea, one problem is that, I mean, mostly the informative point, they are near the decision boundary if you think about this three classification problem. But because of the randomization, it try to select a point, it still try to select some point that are non-informative. Non-informative meaning that it's really the inside of the decision boundary. Still, yes. So that's why sometimes you can select some non-informative point. So it's efficient, but the performance-wise, it might not be that much good sometimes. So
Can I ask a question?
Yeah.
How much of this one, which part of this one is your work?
oh yeah, this one is my work is the next one, the balance entropy part. So this is the balance entropy is my proposal or the new idea how to select this point, the point in this kind of classification problem. And then so this is the previous research up to here. Then balance entropy also try to achieve those three aspects. It's a linear time algorithm, but still it can achieve the diversification and also the maximizing the information gain. Maybe I cannot say it's a really maximizing at the 100%, but if you look at the selection of the balance entropy, then it actually follows the decision boundary. So the selection is following the decision boundary, but still it's really diversified along the decision boundary. So there's some randomness also there in the selection, but really good thing is it's not exactly, I mean, doesn't select the point really inside the decision boundary. It just trying to follow the decision boundary. And then if you choose the point, then because they are so near the decision boundary, they are very informative as well. So it can achieve those three aspects simultaneously. That's why it shows the good performance in the active learning.
What kind of assumptions do you have on those points? Because here they are quite separable, right?
Yeah.
So if you have like these two color cluster, even some intermixing, which is very common in the wild, so then how will this going to work?
They are into it. So still, I think it will work because it actually choosing. I mean that the balance entropy. Actually, I didn't try to design in such a way, but then when try to think about it's sort of sort of coincidence when I try to come up with that formula and then try to see what happened in the decision boundary. That's how I observe this one. So still I would say I need to explore more, but even though they are intermixing together, but because I see that the formula, if you look at the formula, it still try to select a point near the decision boundary, just following the intermixing decision boundary should be working. Yeah.
So are these like TSNE embeddings of a more complex system, or this is actually a two-dimensional data set?
But it is just a two-dimensional system.
Do you consider that a difficult problem?
Oh, this one is not that much difficult, but I really want to understand as a toy example. Yeah. So then I was trying to experiment more like the large the image data scale, like not only the MNIST, it can be C400 and also the tiny
I mean,
image.
MNIST is itself a toy data set, right?
Yeah. So
So
I will give you some, I mean, at least I tested this idea up to like tiny ImageNet, but then we also tested in the semantic segmentation. So in every case, still we saw a lot of benefit. So that's why I'm saying like in semantic segmentation, if you apply the same idea in the pixel level, then it will improve almost like 99.99%, as I can definitely with high confidence. Okay. So so this one is there. I just want to give you some some idea how this balance entropy is working in the decision boundary. So then in the theory in the active learning, if you look at the paper, then the most important part is if you I mean the mostly the points near the decision boundary, they are very informative. But then if you select the point on the decision boundary, they are very noisy. So we have to be very careful when selecting the point. The key critical aspect is we have to select the point a little bit far away from the decision boundary, but not too much far away. Also, if you too much far away, they are not that much informative. So informative is really about something like starting from noisiness and then the informativeness increases and then goes down again. That's why we have to select the point a little bit far away from the decision boundary, and then balance entropy sort of achieve this kind of the spirit automatically. So that's sort of coincidence, I would say. That's why I spent a long time to justify this idea is really working in the active learning. It takes some time to convince the reviewer why this idea is very important or is working in the active learning. But then, eventually, I was trying to able to give some understanding about this measure and also the empirical evidence about how it is really working well, the active learning perspective. So, okay. So yeah. Um, okay, let me just think about. Okay, so I just want to check the time. So just give you some idea how I try to quantify the uncertainty. And this is really just basic level of introduction of Bayesian neural network. So then, I mean, mostly they quantify the uncertainty. People just follow this way. For example, if you have the X-ray images, and then if we have a neural network, then we can apply the dropout or the Laplace approximation or variational dropout or a lot of different idea. We can produce some 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 probability distribution instead of the single probability vector. So then in my case, I would just simply apply the dropout, and I can just generate some probability distribution. So then mostly before like softmax, then we can assume that it will be something like a multivariate Gaussian distribution. Then if we apply the softmax as a probability output, we can just think about some probability distribution. But then my assumption in this case was, okay, this after the softmax, it seems to be following some the beta distribution. So then that's the sort of starting point of in my the developing the formula itself. So then there was some literature. Actually, it was more than now the 40 years ago. The David McKay in the UK. So he he actually had some similar idea. Eventually, I found some paper, and then at that time he tried to use the Laplace approximation. Then there's still some 100%. Maybe it's not 100% match, but still uh, it's reasonable to assume that this kind of the Gaussian plus softmax, the output distribution. If you're only looking at the marginal, we can still assume that this uh, reasonably assume that each marginal just follow the beta distribution. So that's a starting point. And then given this beta distribution assumption, I was trying to look at the histogram of the softmax output after applying the softmax output. Then this is the MNIST example. But then if you look at the histogram, then if I just try to estimate the beta distribution parameter, then I found that they are pretty much well fitted. Yeah. So I mean, there's some edge cases, but in most cases, it's really a good approximation by applying this beta distribution. But then the one good thing in the Bayesian probability is I can just match the mean and variance of each histogram of each marginal, then I can generate the probability, the beta distribution parameter. But then in the Bayesian perspective, beta distribution is a conjugate family. So we can naturally think about the posterior probability. So then that's what I call is a PI plus.
So what is the marginal? So you have the joint probability distribution
Yes.
of what? What are the random variables?
Classes
or something?
Yeah, classes. So
Yeah, you have, in this case, you have how many classes? 10?
yeah, 10 classes.
Okay, so you get the joint distribution by, doing the
Yeah.
out, you get some distribution. And you are saying you can get the distribution and somehow get to the beta distribution.
Right.
From beta distribution, you get the marginal for each of the class.
Right.
Yes?
Exactly.
So then what you do after that?
Yeah. After that, okay. Actually, so if you look at here, if I only consider joint distribution after softmax, the natural distribution should be the Dirichlet distribution. But then at that point, I was more focused on this marginal. But then because I also tried the Dirichlet distribution and tried to apply the similar idea, actually it turned out that that idea didn't work. So then after I tried this marginal focus the formula, and then actually I observed that this idea is working.
So what's the main point? So
Uh-huh.
it is in context of the active learning.
Yes.
So you want to select a sample for which you have, the high uncertainty and you want a oracle to label it, right? So you're saying you're doing all that thing.
Yeah.
And that is better way than
Yeah.
tradition.
Okay. So then let me just give you the idea of this the formula in a little more detail. So then the people, I mean, I talk about okay, mutual information is epistemic uncertainty, then conditional entropy is the aleatoric uncertainty. But then one of the missing information measure is the joint entropy between the model and the label. So then when I try to, but still, given the beta distribution assumption or Dirichlet distribution assumption, I can write down the formula of the joint entropy. But then nobody actually was talking about the joint entropy of those two, the structure model and the label. But then I write down the formula of the joint entropy first. And then I apply that joint entropy with the Dirichlet assumption because it's sort of Dirichlet. If you look at the joint distribution itself, it will be the Dirichlet. If I apply the idea of the joint entropy instead of this marginalized one at the time, and then actually when I tried it, it didn't work. But then I was trying to think about some sort of upper bound of that joint entropy. That is exactly the denominator, the enumerator of this formula. That is the upper bound of the joint entropy is this formula. So then when I try that one, it actually then if I'm looking at the formula equals 0. I mean that's sort of try to trial and error. I just try to understand what's going on because I have some sort of idea about, okay, maybe the joint entropy will be working, but then but still didn't have much understanding about why this joint entropy is really, really working. But then also upper bound of joint entropy is really, really working. So that's why I trying to explore more and then try to give some explanation about this formula. And then suddenly I have to add some denominator by using some applying the Fanos inequality. So then that's how this balance entropy formula just appear. So okay, I cannot say, oh, it's really, really, I understand this formula 100% perfectly, even though I try to design this one. But main motivation at that time was I was trying to think about joint entropy between the model and the label, and then try to look at the upper bound. Then that upper bound seems to be very, very meaningful. And then and then what I found sort of at that time empirically was this joint entropy equals zero was very, very informative in the active learning. So then I try to plot the decision boundary, the selection point, and then really uh, that nears the balance entropy 0 points are really following the decision boundary, and they are automatically the diversified. And then if I apply the apply the fairness inequality, actually I can give some interpretation of this formula. So this interpretation is really about, okay, so if I add the point as a next step label, or if I add that point the next step in the active learning, so then the question is, what is the sort of the error probability after the acquisition? So then actually if you look at this formula itself has some range from negative infinity to one, but then I can interpret this formula as a sort of generalized probability. So then because it's a less than or equal to one. But then the one problem is can be negative, even though it's a negative, but then if I think about this formula or this quantity as a generalized probability, but then there's some threshold. Then if the probability is positive, that means the error probability naturally appears. But before the zero threshold or negative probability, it might not, I mean, the error probability might not appear. So because of that, I think this threshold zero is very important. And then if the error probability is too high, that means the point itself is very noisy, sort of a high aleatoric uncertainty. And then also near 0 point, it still is informative, and because it can start to show, start to have some sort of error, that means it's still informative, but it might not be that much, not much I mean, it's still very informative, but it might not be that much noisy. So that's why the zero error probability is very important. So that's sort of, yeah, by applying some the Fanos inequality, how I was trying to interpret this formula. It's sort of the post-processing after I tried to think about joint entropy, and then try to apply the active learning, and then try to really understand what the meaning of this formula. And then at least I have this kind of interpretation, and this interpretation it's not 100% satisfactory, but this still give us some idea as a generalized error probability. Then the zero threshold is a really, really
So at the
important.
end, then you have a better active learning method to
Yeah.
find the uncertainty.
Yes, yes. So the better means that it's informative, and also as I observed in the empirical the decision boundary point, it's automatically diversified along the different class the variable, and also this formula does not involve any pairwise computation. It's just standalone formula. So because of this linear time, the formula, so it's very, very efficient. I mean, even though it requires a little more dropout, but still, it's at a large scale. I would say that, or the algorithmic scale.
Somebody wants to forge your method, right?
Uh-huh.
So there's a neural network, you drop out, you get one estimate, another dropout, you get some distribution.
Yeah.
So you take the distribution, then you're saying you do soft mix, and you get a beta distribution.
Yes.
Yes. And then what you do with that?
Yes.
What's the method? After that, Once I get a better distribution, how do I proceed to finish the job?
Okay, so once I have the beta distribution, I have the beta parameter, then I can automatically find this posterior beta distribution as well. But then after that, actually, let me show you. Actually, this one I can calculate this formula, as a closed form. I can automatically just plug in this beta parameter. I can get this answer immediately. So this is the closed form solution. I was able to derive even starting from the beta distribution assumption or the Dirichlet. So then I can get the closed formula.
So to get uncertainty for the particular sample, you put in this formula, you get number based on you decide.
Exactly.
What to be better.
Yes. Yeah. So yeah, the beta and gamma
So this
distribution.
X is like a new point that is coming in.
Yeah, it's a new
It's a
point.
new point coming in based on the this prior dropout that I have already measured.
Yes, yes,
Okay.
yes.
Okay.
Because I don't have a ground truth label yet for this, but still I can capture this balance entropy for each point.
Okay.
Yeah.
And do you need to change the dropout parameters as well?
I mean that depends on the choice because
How is that affecting this?
Uh,
Because if you are changing the dropout, that is also playing with the randomness
yes,
in the network, in
Right.
the decision process.
right.
So how does that change the
Actually,
parameter?
I mean, there's still some selection randomness, but still I didn't see much effect of the different performance because even though I reduced the dropout rate, for example, but in my case, mostly I use 20%, but still if you use the 50% of dropout, but then maybe you have to increase the number of sample because of high dropout rate. But still I can estimate this beta distribution parameter, but still pretty much very robust. Yeah, I mean, especially the active learning performance, I cannot say they are the same, but I mean, empirically, I can say yeah, it's robust, but I don't know the exact theory how to answer your question with the robust theory yet. But empirically, I observed that it's pretty much robust to with respect to the different dropout, the ratio parameter. But yeah, for example, like yeah, I mean the number of sample size actually didn't matter much when I tried this idea. I mean for the paper writing, I wanted to use a high number of the dropout sample because I really need to convince the reviewer. Okay, my experiment is really thorough, and then I tried to use 100 sample for each point. But then in the segmentation case, when we tried it, typically we use 20 sample was enough, or sometimes the 5 sample is enough as well. So it doesn't require that much number of sample. But once we have applied the dropout, then I can estimate this beta distribution, and then I can easily calculate the calculate the balance entropy.
So how much was the performance improvement on the?
Okay, so let me give you the output and the answer. I think yeah, a little running out of time. Okay, let me make it a little faster. So this is the simple example. One is the MNIST case. The other one is SBS. And very big now is a really toy example. But then in this exercise is really about measuring the informativeness first, because the acquisition size one means for each active learning iteration, I only want to choose the single point. But then here I want to remove the diversification effect first. But then that means it really capturing the maximizing the information gain. And then if you interpret this plot, the plot is upper than the other, that means it's better than the other method. And then the bulk balance entropy, mostly bulk is more about maximizing the mutual information. But then still there's some the relationship between the point, but still the balance entropy actually capturing the high informative point very well. So it's really at the top of this one. And then if you look at this case, you don't need much point. It's almost like 300. It's actually less than 300 points is enough to achieve the maximum the accuracy with the MS data set. So SVHN is a similar, but it's a more diversification scenario. So let me make it a little faster. So the other one is the C400, but I added the two more images. So it's a redundant data scenario. So it's more about capturing the diversification. Then in the Google, it's now still outdated. But then the batch is really about the diversify, the selection, and with achieving the high informative, high information gain. But if you compare those two, balance entropy actually eventually they are performing very similarly.
So what is the x-axis of this?
X-axis is the number of the data point, the number of images I added in the classification. And y-axis is the accuracy. Yeah, sorry for missing this explanation.
Those you unlabeled.
Yeah, unlabeled data, and then the accumulated unlabeled data. So there are some batch for each acquisition. I added the 500 images. So and then gradually adding more data at each step, and I see the accuracy improvement along the way of the.
And that is also like the part of the total data, right?
Yeah, total
Maybe
data.
you should put a percentage sign on this.
Oh, yeah.
So it should be very
Right.
self-explanatory.
Yeah.
Thank you. Yeah.
Yeah, yeah. So I think because it's 3 times, so it's a C500 is more like 50,000 images. So then because the augmented more like 3 times, so that means 150,000 images. So it's a 3 times. So then if you only use like 250, no, 25,000 images, it's almost achieved or 20,000 images, you can almost achieve the full accuracy. So you can reduce the image size significantly, but still, so batch is actually computationally more demanding, but that's why it initially shows a good performance. But eventually, the balance entropy actually catch up with that performance. So they are very similar, but a good thing of the balance entropy is it's a linear time the algorithm, but still it can achieve very similar performance like that. So, yes.
Studying for
Yes.
things to be. Acquisition size means that you are gonna sample, what you are gonna sample 500 of them, 500 points which you assume they are not labeled.
Yeah, no. Not labeled is more like initially it's the 150,000 images, not labeled. And then each time I'm adding 500 images, labeled images.
And in order to choose those 500 images, what are you gonna do?
I calculate those kind of uncertainty measure.
For all the 15,000.
Yeah, all the
For all
15,000.
the 15,000 you calculate.
Yeah, so then after that, I just look at the rank of the uncertainty, and then based on those
If
rank.
you would apply this one to ImageNet, you would calculate the uncertainty for 10 million images.
Yeah, that's.
And then you are going to search that vector.
Yeah, so the
Then
point like.
search that vector for choosing the ones which you choose to label.
Exactly.
Do you have a certain thing of what cost benefit, like how expensive does a label have to be in order for this to be? So wait a second. For each of those images, you have to take your existing network, run a simulation with different random seeds for the dropout in order for you to get an approximation of the output onto which you fit a data distribution, find the alphas and the gammas, and then you repeat this one for 10 million images.
Yes. Yeah, that's I have to do it again.
And then you have to search that 10 million.
Yeah, so search that one again.
When you choose the 500 of them, which are the top according to whatever is
Exactly.
and then you put this one.
Yeah. So in some sense, in this domain, those kind of computation is still sort of cheaper than the human labeling cost. But still, even though you search the 1 million image space,
not an image labeling, though, right? Has to be something like running a cancer drug or something in order to do this thing. This is not, it cannot be that cheap.
But maybe also one thing is that it is better to have the time for the method to reach the accuracy. So like CPU time or also time.
So that one is actually included in the paper in the appendix. At least you can see some idea in the appendix. Yeah, there's some, but still it's a very faster. I shall try to augment like 20 times of this. It's more than 1 million scale, but But still, yeah, at that time, it's still much better than the
What is the index there for the 065?
this one.
Like the number.
The accuracy.
Yeah, but what is the bottom and what's the high one?
Oh, starting from is the 15% because if you use only the 500 images, you can achieve like 15% accuracy with the
The
C400,
high one.
and then it's almost like 66.
And what is that line there?
Now this is the if you add all the images, labeled images, this is your full accuracy given your neural network. But
Wait, you are
yeah,
exceeding,
it's still going.
you are exceeding the,
Yeah, in this case, actually exceed one. Actually, it actually reduced the noise as well in some sense. Because the C400 entire image data set still has some noise. So because of that, it actually exceed that the full accuracy
and
level.
what is the mechanism through which this thing would exceed the,
Actually, removing the sort of noisiness. That sort of, yeah, we observed that this active learning is also useful, removing some uninformative or the noise data as well. Sort of.
so you are fine tuning an existing, you're fine tuning an existing.
No, starting from scratch. Or sometimes it can be pre-trained model like ImageNet, but it's sort of cheating, so I didn't try to use that one.
So like the extra 500, what are you doing with them? You got extra 500 labels and you fine tune whatever you had before with those.
Fine tune with 500 and then.
So let's say somewhere in the middle you have
Yes.
you have 10,000,
Yeah,
let's say
okay.
there, right? Okay, you have 10,000, and then you are gonna do another one. Now you have extra 500.
Yes.
So what are you gonna do?
Oh, actually, yeah, there are two definitely. And then in such a case, in active learning paper, I just starting from scratch, not the fine tuning. So I just try train the models like 10,000 plus 500, and retrain the model from scratch. So that's how I wanted to generate the accuracy curve, because that's sort of the at that time typical way to show the output. But then also in tiling in that case, also because in real scenario, we also want to fine tune adding the more point and retrain the model. So it still works, yeah, with that scenario. So that's sort of
each of those has been trained from scratch.
yeah. I mean, in all these plot, yeah, I try to train the from scratch for each iteration. But also fine tuning scenario, it also worked. That's I can say, yeah. Because the problem of fine tuning is you already train a model with the previous 10,000 images, and then after at the fine tuning stage, you might train with only the 500 initial additional images. That's one way. The other way is you can also retrain the model with 100,000 plus 500. But still, in such a case, there's some overfitting with the previous image, previous information. So because to remove that kind of the scenario, we just try to train the model from scratch with all the selected data point. So I mean that's definitely there's an issue to think about it. So I think yeah. So just want to quickly give you the recent one. This is more about curriculum. If you have some. Yeah. Okay. So yeah. So this is really the recent topic. I just want to give you the 5 minute talk about the how I wanted to apply the Velas entropy in the large language model alignment training. But then I wanted to focus more on the curriculum learning. And if you look at the recent the alignment training, the paper, they are really nowadays many people just talk about it. We can reduce the preference data the size in the language model training. But then because I already did active learning and try to reduce the data, so I wanted to more focus on the order of the data during the training. That's sort of the curriculum learning. And then our intuition is that as a human learning perspective, sometimes okay, so we are learning something new concept, gradually adding more difficulty. So starting from very basic concept and then adding the more difficulty. But that's sort of yeah what I described the left hand side. And but right hand side is another way to think about it is if I'm already very knowledgeable, And then tomorrow is sort of the midterm. Think about the exam. What's a better way to achieve the highest score? So then maybe, okay, I want to just focus more on the most difficult problem first, and then maybe it's better to just reduce the difficulty level step by step. So we can also think about both ways, increasing the uncertainty or difficulty level, and then the other way is decreasing the difficulty level. Then just try to think about how this ordering actually affect the language model, the alignment training. So it's not about pre-training stage, it's just more about alignment, meaning that in the ChatGPT, by applying the reinforcement and human feedback, they typically have the preference data, which one is the preferred or non-preferred. If you have a binary kind of this data set output, then we can train the model, given some the preference data. So then this just show, I mean, recently we submitted the HTML. I don't know if it will be accepted or not, but then this radar plot shows why this curriculum is really, really important. So if you choose the wrong bad curriculum, there are 8 different aspects of each language. There's a benchmark, it's called the multi-term benchmark, but then mostly not about the math or coding. But reasoning and wordplay writing, we really want to improve that kind of aspect by applying the alignment. But then if we choose some wrong curriculum, actually we really reduce the performance of the language model. It actually is not very helpful. But if you choose the right or good curriculum, actually it can improve the language model's performance. So that's why this curriculum is very important. And then we have to be very careful when we choose the order of the alignment training. So this is good, and it's just some example about the bad curriculum example. But if you look at the example a little bit, in most cases, it just gives you some very passive answer. Okay, in any case, I mean, this alignment is designed to generate some output or answer like, okay, if it's toxic, then just try to refuse to answer. But in this case, in any case, regardless of the toxicness or anyway, that it just try to refuse the answer. I'm sorry, I don't know. I'm sorry, I don't know. That's sort of, but depending on how you choose the order of the point. So yeah, this is the sort of framework, and then still trying to explore aleatoric epistemic and balance entropy. And then because the preferred data, we can reformulate this problem as a simple binary classification problem because this data is a preferred or chosen or the non-preferred as a rejected. So I can easily translate the problem into a binary classification, and I can quantify the uncertainty of this preference data. So then I just tried the different ordering. Ordering is more about the random order, and then the increasing epistemic, decreasing epistemic, increasing aleatoric, decreasing aleatoric, increasing balance entropy, decreasing balance entropy. So sort of we can think about different combination. And then if you look at this, the result with the llama 7 billion case, then actually what I can say here is the both direction. In this case, aleatory case, the increasing aleatory gives us the good performance, but also decreasing balance entropy actually gives the good performance as well. So there are some, two different aspects. One is a single score benchmark. The other one is sort of pairwise comparison of the output with the other benchmark with baseline the model. But then in the single score perspective, decreasing the uncertainty direction actually give me the best answer in most cases. And also the increasing the aleatory case actually is much more better than the pairwise comparison. So I just give you some idea about that. If you I give you the example like, okay, tomorrow is the exam. If I really want to improve the score, I can, it's much better to focus on the difficult problem first. Okay. So that's the way and I can achieve it. And then the aleatory increasing is more like starting from the beginning or it's easy example, increasing the difficulty. That model can be much more well-grounded. So, okay. So I just want to make some conclusion. So I just want to finish this. So I just give you the overview of the why uncertainty is very important. And then just want to give you some example of the application, active learning and curricular learning. So, and then, yeah, I'm really excited about this position and then looking forward to discuss more about the new idea. Thank you so much. Yeah, sorry for the voice line.
I think we have taken enough questions. Yeah, I don't lunch. Okay. So we are going to the lunch if you want to join. Yes, sometime.
No, I didn't say.
No. So, I think that's not just about. Yeah, that's all. I'm not exactly like. So, yeah. That's fine. So, next time I remember that. So, yeah. Will come in and those candies are under all the course. So, as I share all of the if I would like to be institution, yeah, like, I remember, show something. No, you were in